All right. Everyone ready for machine learning? Woo! I didn't actually want that. Stop. All right. So today I'm using a microphone because yesterday I didn't, or last class I didn't, and the online lecture had no audio. But today it will. So hi, people online. I don't know where the camera is there. So today we're going to be doing a little bit of actual machine learning. Crazy, I know. I also have a little bit of a request for everyone. So if you are not using your laptop to actively take notes, I'm going to ask that you close it. So this whole, using this room and doing lots of group stuff, part of the point is that you get to talk to each other. That's really good for learning, really good for talking to people, which we could all use a little bit more of. And having a laptop up, I feel like kind of isolates you. I'd like if you guys didn't have them up. Anyway. If you're using it for notes, so that's fine. And if you are using it for notes, I also just uploaded the slides online, so you can go look at it on Moodle and Piazza. All right, anyway, done with that. Oh, also, Happy Lunar New Year to anyone who's celebrating. It's Year of the Tiger now, as of, I guess now, if you're in China. I am a tiger, so that means that I am either 23, 35, or 11, I guess. So up to you to decide which one that is. All right. Cool. So let's talk about what we talked about last time. So first up, AI. We got a little ball here. And machine learning is a subset of it. In fact, a very small subset, a very recent subset. A little bit less recent than you'd probably guess, but pretty recent. We also talked about how we're going to be using data to tune parameters which express some model that perform a function. Last class, we talked about linear regression, and we're going to continue talking about linear regression, but with a little bit more math. So here was the notation that we used. Our inputs are going to be labeled x, and we're using this weird superscript to mean which data point. Important you guys don't get mixed up about that, because we're going to have a lot of subscripts and superscripts going for a little bit. I'm going to remove as many of those as possible by using a linear algebra notation, but there's still going to be a few of them, so get used to them. All right. So we also learned that when we are given labels of the data, so here we have y being our actual labels. So we're given input, and we have a true output. If we're given that, and we're able to use those labels, that's called supervised learning. It's not the only type of learning, but it is the most common, and it's the one that usually when people talk about machine learning, they're talking about. Less so these days, but a lot more in the past. All right, and here was our current diagram. This diagram will change over the semester. It'll get very funky and stuff, but for now, we take in some input, x, q, so this is the qth data point, and we want our model to produce yq. In reality, it produces some y prime q or some y hat q, which is what we're going to call it later, and we have to compare that. But for now, we say that we want that yq, if possible. Ideally, we get it perfectly, like we did last class. All right. So last class, we talked about these very easy linear algebra examples. So let's go over the same one. I just want to remind you all. So we had this model, which was w1x plus w2x squared plus b. And we got this data. And we were able to hand calculate, although it was somewhat difficult, that our parameters, our w1, w2, and b, should be set to the following values to express this function exactly. Now, we didn't talk about how at all we might automatically learn those, but we were able to do it by hand. So now let's look at something that would approximate real data. This is made up data that I made up, but I want you to show you what some of the problems we start to face are. So we start with our input, which is hours of sleep, 1, 2, 5, 6, 8, and 12. God, 1 and 12. Oh. I'm somehow both of those, actually. So now we also have our labels, which are the scores on the final. So with this number of hours of sleep, these people got these corresponding scores on their final. And we can plot this data. So let's take a look at it. Cool. Now, the question is, you can see pretty immediately that this is not linear. This is not a line. They don't totally line up. So if we were to put a line here, that seems pretty good, right? That's like, it's really close to them, but there's that one that's pretty far away. I don't like that. How about this one? This one lines up perfectly with a few of them. That's great. But again, we have this really bad outlier, and now 1 on the other side. Well, what if we try to get rid of those and we do something more like this? Well, that doesn't really line up to any of them, and it doesn't look that good. So the question becomes, how do we decide which one of these lines is the best? Anyone have any ideas? Yeah? Least deviation. Okay, so that is good, and we're going to talk about that later. Okay, so let's keep going and let's see what happens here. So we're going to introduce a very important concept. This is one of the most important concepts that we're going to get in. This is the most important concept in the whole lecture, and it's one of the more important aspects of supervised learning. So what we want to do is we want to have some function that will be able to determine how poorly our model is doing. And we're going to call this a loss function. There's also, like, people might call it an objective function. Generally, if you call it an objective function, then you want to maximize it. In this case, we want to minimize it. We want for our model to do as little poorly as possible. So we want to minimize the loss. All right. So here's our data, again. And I'll ask you basically the same question, but I'm going to have you guys talk in your group. A naive approach to how we might want to, like, what sort of loss function might we want if we're doing something very naive? We're saying we just want to minimize something. What would it be? So talk in your small groups and try to come up with something, some function that we might want to use here. All right? By the way, I'm seeing quite a bit of people being just talking to their whole table. I really do mean when I say small groups, so just the people next to you, like 2 or 3 people, all right? Want to give everyone a chance to talk. All right. I think that's enough time on that. So, anyone want to tell me what they're thinking? There's a pretty straightforward answer that we talked about a little bit, but what do people come up with? Remember the whole awkward silence thing? I can still do it. Yeah. Summation y hat minus y divided by x squared. So we're going to take the difference between each of these, essentially the prediction and the point at every one of these x's, and then square the difference. All right, that's a perfectly reasonable thing. Anyone else have anything else we might want to do? I'll go with the second option being exactly what you said, which was deviation. I assume what you mean there is distance from the line, just straight up L1 distance, L1 just being the simple distance, L2 is squared. And that is absolutely what we're going to start with. So we're going to start with that, and let's formalize it a little bit. So we're going to take distance from each point. So that's the distance of the line from each point, and we're going to sum them up. In particular, it's going to be exactly this. So our loss function is going to be, given some actual label and our prediction, we are going to sum, so the big Y and the big Y prime are going to correspond to all of our predictions, all of the data points. So it'll be all of the real data points and all of our predictions at those same X values. And we're going to take the absolute difference between them. It's important that we use the absolute, and we'll talk about why. And then we're just going to average them. So that's going to be what we call, so just to get a little notation, the yn is the nth piece of data, and y prime n is going to be the output of the model on that same input, on the nth piece of input. And this loss is going to be called mean absolute error. Pretty straightforward. Mean, because we're averaging over all of the data points. Absolute, because we have the absolute value. And error, because it's the difference. Very straightforward. So, how are we going to minimize this? So, we now have some representation of how badly our model is doing, and we want to minimize it. Now, answering this question of how we minimize it is essentially the whole rest of this section, is how we minimize that as best as possible. Now, let's talk about a couple other losses just to get some ideas. And mean squared error, which is exactly what was said over here, is going to be the average of them, but instead of taking the absolute value, it will be squared instead. Now, I want you, again, to talk in your small groups. How is this functionally any different than mean absolute error? If we train a model to minimize mean absolute error, say we have some black box training thing that we can do, versus one that's trained to minimize mean squared error, what would the difference be? All right, talk in your groups. All right. I think that should be enough time for that. It's a pretty simple question, or relatively straightforward question. So, anyone have any ideas? Yeah?
Outliers are punished more? Like the further you are, the more you're punished?
Outliers are punished more. If we just look at doing the summation, if we imagine we have one very big outlier away from the model for the MSE, then we can imagine that that error will then be squared and added together and will essentially override everything else. It will be the biggest error. If we have a very far outlier, you can imagine, just for an extreme example, which means that if we were to minimize it, our model that is trained on MSE will prefer to have the model predict straight through the center of the data. It wants no outliers at all. Whereas MAE will prefer an outlier. If it has a big outlier, that's fine, as long as we can minimize everything else and that doesn't totally override everything. So functionally, and this is the important point of all of this, functionally, loss functions will determine what model you end up with. It will determine what you are actually training to do. So this is the fundamental first step of having an optimization algorithm, is having some objective, having some loss function that we are trying to minimize. So just make sure that you're comfortable with this idea. It's relatively intuitive, but it'll get a lot more complicated pretty quickly. Yeah?
So in specific situations, will we use one over the other?
Yes.
Okay.
So there are, in fact, you could think very simply what our goal is as a person who's making this model. If we want there to be no outliers, then we would use MSE. If we don't care about outliers, a couple outliers, then we use MAE. So a lot of it is determining what our actual objective is in the real world, and then finding a loss function that reflects that. And of course, loss functions can get much more complicated than this, but for now we're going to just talk about these. All right, so now I want you to, again, and this time just individually, for a little bit, try to see if you can think up any other loss function that you think would work. There's so if you can think of a very simple one, that's actually perfectly fine. Thinking up a good loss function is a very hard problem, and an open problem in machine learning. So don't worry about not being able to think of a good enough one, but just think about it for a little bit. All right, now go in small groups and talk about what you're thinking about. All right, all right. So I'm glad to see that people seem upset when I tell them to stop talking. Anyone have any loss functions they want to share? Kind of difficult to do anything other than distance, right? Yes?
So based on the MAE, we can do it without using the absolute value. We can maybe counting the bias and maybe whether it's below the line or above the line. Does that make sense?
So you're suggesting, sorry,
The same formula without using the absolute value.
okay, so taking MAE but without the absolute value.
Yeah.
We're going to talk about it in a second, but I'll have you all just think about that, put that in the back of your mind, think about whether that's going to work or not, and think about all that. Anyone else want to share one? Yeah.
I don't know. We were discussing this in table, but nobody is showing up, I would say.
Okay.
So we were thinking about we can have certain threshold from our prediction where we don't count the error. And after that threshold, we punish the model hard, like normally.
Okay, interesting loss function. So essentially, if it's within some bound, you don't care. And if it's outside of that bound, then you do care. It's an interesting thing, and we are going to see something kind of similar to that next lecture, not today. But generally, those aren't put in the loss functions, but it's an interesting idea. Yeah, perfectly reasonable idea. All right, cool. Well, let's see what the properties of a loss function that are valid are. So there's a couple things that make a loss function actually able to perform the way that we want it to as a loss function. And there are three main things, and we're going to go through them. One, the minimal loss should correspond to the best model. That's relatively straightforward. If there's a line of best fit, then the minimum loss should be also the best line by our same definition. This is relatively straightforward. It is more just defining what a loss function is. Secondly, the loss function must be defined for all outputs and labels. So there can't be any loss function where the loss is undefined. Notably, this would be a division by 0. So there's some loss functions you might be able to construct, and then you'd end up seeing that you divide by 0, and that doesn't really work unless you're very much willing to go through a ton of hoops to make it work. And that would essentially be redesigning it to not do that. And number 3, and weirdly, and we're going to talk about this later, the loss function should be differentiable. In fact, has to be differentiable for a lot of learning techniques, but it should be differentiable. So we want to think about loss functions that are differentiable. Now, you may have spotted, if you're pretty quick on this, that we're using mean absolute error, which is the absolute difference, which is not differentiable. It's essentially a v with a sharp discontinuity. That is sort of an outlier, weirdly, in the realm. It's one of the easiest loss functions to talk about. And one of the reasons that we can avoid this is that we don't actually need to use stochastic gradient descent to do it. And we can also approximate it by just treating that as not a discontinuity. So this is a case where we can have a non-differentiable one. I'm not going into the details of it too much because it's not important yet. We're going to talk about it later. But there are cases where it isn't differentiable, but it should be. All right. So now the question, this is the example that you came up with. Would this loss function work? So under these three conditions, would this loss function work? So this is mean absolute error without the absolute error bars, or the absolute bars. All right, talk in your groups for a couple of minutes and see if you can decide whether it will or will not work. And why? Okay, what are we thinking? Oh, not yet, I guess. People want to talk? Yeah. All right, give me 1 second. Yo! All right, that's time on that. So let's hear what people are thinking. Let's do a hands raised thing. Who thinks that it will work? Nice. All right. And who thinks it won't work? I think that's everyone, just about. Some people not raising at all. Okay. So someone who thinks it won't work. Why won't it work under these conditions? Yeah.
Because if you're taking the sum of the distances from all points, you could have one that's like, say, like positive 5, and then one that's like negative 5 below the line, and then that'll just average out to a loss of 0.
It's actually okay. If that's what we want it to do, it's okay for it to do that. That's not exactly what's wrong with it, but there is something that's wrong with it. Anyone else? Yeah.
We find out that the first bullet isn't always true. Like there could be some lines that are really bad that still have the minimum loss.
In particular, what is the minimum loss of this? Of this function right here? Here in some zeros. Is it possible for there to be a negative value of this? What would that mean? That mean that the prediction is less than, on average, the actual labels. So what would, or is above actually, sorry, this one's backwards from, anyway. So it would mean that the actual predictions are above, right? So what would happen if our predictions were all positive infinity? So yn minus positive infinity is negative infinity. So what this model would actually learn to do is predict as large outputs as possible, and that would minimize the loss by sending it to negative infinity. We solve this problem by putting an absolute value on it, because then it will be the actual distance. All right? So this is an example of one that seems intuitive but won't work. There are a lot of them. This one's one of the more simple ones to conceptualize, but that's something you have to look out for. So definitely look out for whether or not it can go to negative infinity. That's always is an indicator it won't work. It will violate the first point no matter what, if it can go to negative infinity, because then it can change. I suppose there might be some really weird case where it would work, but yeah. Yep.
Just to clarify, y to the n is the point on the best fit line, and then y to the prime n is?
Other way around. So y, a normal y is always going to be the label, and y prime is always going to be our prediction. Just for clarification. In the homework, we're going to use y hat instead of y prime. They're the same thing. Y hat just looks a little bit prettier. I don't want to do it on here, but we can do it on LaTeX. Anyway, cool. All right. So This brings us to the actual very interesting core of machine learning and supervised learning in particular. How do we minimize this? So we just invented some arbitrary loss function. How do we minimize that loss based on our model? So first, let's start with how do we find the minimum of a function? Just some random function. Anyone want to talk about it? Yeah.
Take the derivative,
Take the derivative and
set it to 0.
set it to 0. So that's the very basic way that we might want to do that. So that's the very first thing. So we could imagine that we could, hypothetically, set our parameters w such that the derivative of loss with respect to those w's is 0. And then check all of those if there are multiple and find which one's the minimum. This works in cases where we have a convex function. It happens to turn out that linear regression is always convex, so we can actually do that in this case. We're not going to because that's not this class. But in a case where we only have one minima, this is perfectly fine. Or even a reasonably finite number of them, we can check them all. It's all good. But we want to think about a case where we have multiple minima and we don't want to check them all. Maybe it's too difficult to calculate what w should be to set this derivative to 0. Maybe we don't have time to check them all by hand, and maybe we want to do it automatically. Or maybe we can't do it automatically. So now we get into one of the most interesting parts of the lecture, and this is going to start with a little bit of math. I think you all had to have taken 233, so this is just going to be a refresher for all of you. So imagine we have some function here. This is going to be a three-dimensional function, so we can visualize it a little bit better. You'll notice that the x and y axis, so the two bottom axes, are colored as parameters. So those are going to be the values of our parameters of our model. This is a two-parameter model. We could expand this in more dimensions, but then it'd be hard to show. And on the y-axis, or the z-axis, we have the value of the loss function. So if we have some random initialization or some random setting of our parameters, it will correspond to some point on this grid. In fact, it will actually be, with some random input and some random parameter settings, we'd get some point. Now, we have this direction, the direction of steepest ascent, and this is the gradient. So the gradient is the direction of steepest ascent. In particular, it is defined as the direction where if we take a sufficiently small step in that direction, we will increase loss. All right? Maybe the gears are starting to turn about why that's important. The reason that's so important is we have a corollary definition, which is the negative gradient. The negative gradient is the direction of steepest descent. So we always know that at a point, the direction of steepest ascent and descent are exactly opposite each other on any dimensional plane, any dimensional surface. The reason this is important is because if we take a small enough step in this direction, we are guaranteed to decrease loss. So the significance of that statement might not immediately land, but let me explain it. We can come up with some loss function that describes some objective we want on any task where there's an input and an output. We can find any model that is parametric in whichever way we want to represent any kind of function. And then, if we were to be able to move in the direction of the negative gradient just a little bit, we will necessarily do better than random, than our random initialization. And we're able to repeatedly do this. And this brings us to one of the best inventions in AI, gradient descent. You probably have already gotten where we're going with this, but still, it's a good ride. So we have our gradients, the gradient and the negative gradient. And here, I'm going to scare you with a little bit of math, is the notation for the gradient of loss. So this is the gradient of loss with respect to parameters w. In this case being w1, w2, w3, etc. And the gradient is just going to be all of the partial derivatives of loss with respect to those parameters. So it's going to look something like this. And if you're really uncomfortable with that notation, probably look it up and probably try to let this settle in. The partial derivatives aren't that bad, and we're just essentially taking every single one of them, at least all of w. That's all we care about now. So if we have our gradient here, what would we do to the weights to move down the gradient? Anyone? Give you a second to think. All right, anyone have a thought? Sure.
Just subtract the gradient from the log.
Beautifully simple, right?
Weight.
Weight equals weight minus gradient. That's all. So we are subtracting the gradient. So the gradient and the negative gradient are always opposite each other. So if we take the negative gradient, we are going to move in the direction of the negative gradient, which we know will increase or decrease loss. Beautiful. I'm also going to give you a secondary notation. And do be advised, this is secondary notation. So we're going to be using a lot of matrix notation like this. So you see here that w corresponds to multiple values of w. Hopefully this will settle in with you guys and you won't be upset about it in the future. But here's a other notation so that you can maybe justify this. So this is for each of the wi. We're saying wi is equal to wi minus the partial derivative of that particular wi. That is, the gradient of loss with respect to these parameters is going to be the same size as the vector of the parameters, and they will correspond one-to-one. So we can just do a for loop and subtract all of these partial derivatives if we want to. We're going to be using this notation because it's much more condensed, you can see, and it will be much nicer later when we get bigger networks and stuff going on. So I'll remind you of the definition that I just said. It was if we take a sufficiently small step in this direction, we will necessarily decrease loss. Does this equation satisfy that? So think about that for a second and then talk to your small groups and see what you can come up with. All right, talk to your groups now. All right. We're doing another poll. All right? So, how many people think that this does satisfy that condition? Okay? More than 0. I like it. I like it. And how many people think this doesn't satisfy this condition? Okay. Okay. Someone who said that it doesn't satisfy it, why not?
There needs to be some variable multiplied by the derivative in order to subtract it proportionally.
Someone's taken machine learning or something before. No? No? Okay, good idea then. Yeah, you also had something?
Yeah, so it's possible that like the small steps, they're like way too small that we could like be stuck in like a local minima and not like so there's an absolute minimum and a local. If the steps are like really, really, really small, we could risk being stuck in one big local.
That's another interesting idea, and we're going to talk about that later. So, yeah? That is possible. So this is something that I kind of lied about. Not lied, but I kind of left out. The gradient is not only a direction, but also a magnitude. We're going to be able to calculate these magnitudes later on, what the actual values are. But the problem with it is, let's imagine a scenario where we have, this is our loss function. So it's a one-dimensional loss function, right? We only have one parameter. And let's imagine we start right here. So this will be a little bit of a nuance that I want you guys to all get to. The direction of the gradient, let's say at this point, is like so. So you notice the fact that the gradient is not actually a slope. It corresponds to the variables that it's related to. So in this case, it is only moving along the parameter for w. All right? So if we have a gradient like this, we might end up somewhere like at the local minima. That's great. Cool. We're happy. But what happens if we have a gradient like that? What if the magnitude is much higher? Well, in this case, we'd end up somewhere here. And we can see very obviously that the loss increases. So it is possible, if we take too large a step, which is proportional to the magnitude of the gradient, that we might miss the local minima and in fact increase the loss. So here is an exact example of us violating the property that it is always decreasing the loss. Now, what might we do to fix this? So again, think about this for a little bit. What could we do? I'll give it a second so people can think, but I like the idea. All right. I think people have probably come up with at least an idea. Could anyone share with me their thought? I want to hear from a table I haven't heard from. I'm going to do that teacher thing, yeah. How about you guys? Deer in headlights, I like it. Yeah.
We thought that you could start it out small and then make it bigger and bigger.
So make the step size or how, like the magnitude of the gradient, you want it to start small and then get bigger?
Yeah, until the loss function starts going back up.
So loss function starts going back up. And then back down. So I will remind you that we do want it to always, so ideally we do want to go down. So what you're describing essentially is if we have a large loss function, right, and it does skip out of it misses local minima like this, we'd imagine we have a big like setup where there are very deep local minima, and some of them are much, much deeper than others, and some are very shallow and difficult for us to escape. If we have a large learning rate, sorry, if we take big magnitude steps like this, then we might be able to jump out of ones we're in and go to deeper ones. We're able to explore more. We'll explore the loss function a little bit more. And it's a very simple loss function. Imagine there's much more to it. So we're able to explore a bit. So it's a good concept to have a large loss function. But if we were to keep increasing, if we were to keep taking bigger and bigger steps, we would never actually be able to settle in any of the minima. We would just keep exploring. So there's a little bit of a trade-off of exploration versus exploitation going on. And ironically, you sort of found the exact opposite of one of the contemporary answers. Not that it's close, but the one contemporary answer, which is a learning rule called ATOM. So what happens in ATOM is we take large steps first, and then they get smaller and smaller and smaller. So you can imagine we search around until we end up in something that is hard for us to escape in whatever way. And then we take smaller and smaller steps until we go into it. So that is operating under some assumptions if we think that's going to end up at a very good minima. So it's only usable sometimes. But generally, it's a pretty accepted and liked one. So all of these ideas do rely on one concept, though, which is the idea that we are able to scale the magnitude. So that's the most fundamental thing, is we want to be able to scale the magnitude however we'd like. We'd like to be able to take smaller steps if we want to take smaller steps. So this is going to give us our actual formula for stochastic gradient descent, which is a very important thing to understand if you want to know machine learning. Stochastic gradient descent is basically the foundation for all of modern machine learning, and it's very important. So what we're going to do is that we are given a model of parameters, W. We're just going to use W for now, no bias. For now, we're just going to say the parameters are W. A loss function, which takes both the actual input and a label, where the label is some function of the parameters and the input. And a learning rate. So a learning rate is what we're going to call, you might have heard me slip up and say it by name earlier. The learning rate is going to be how we are going to scale the magnitude. And it's very straightforward, the change we're going to make. We are going to now scale the gradient by this learning rate. So you can imagine if we set this learning rate to be infinitesimally small, then we would always satisfy that requirement we had earlier where we'll necessarily decrease loss, and it will. But as someone was saying earlier, that might be a problem, and we can think about that. So learning rate is going to be our first example of what we are going to call a hyperparameter. So the W is our parameters. These are our model that are able to actually take an input and give us an output. What hyperparameters are something that we decide. So we're going to decide before we start training what these hyperparameters are set to. And that is going to stay the same throughout our training. Well, we could change it hypothetically. But they do not get learned by the learning algorithm. They are going to just be decided by us. We call them hyperparameters. We're going to have a lot of them. For now, we just have one, though. So now we're going to directly answer that question that I brought up. Is it possible to have a learning rate that is too small? And why is that a problem? Anyone want to just tell me? I think we've talked about it enough that probably people have some idea of what's going on. Yeah. That's true. So it would take a really long time for us to learn anything. We are taking smaller and smaller steps. We're not going to ever improve by very much each time we do some learning. Yeah. Exactly. So it is relying on the exploitation side of the exploration. You said that it wouldn't be able to find a global minima. And exactly, if we start in a local minima and our learning rate is small enough, we will never escape that local minima. And we are basically guaranteed to be in some local minima no matter what, unless our function is totally flat. So we're going to end up stuck if we have a learning rate that's too small. So how do you decide the best learning rate? Anyone have any ideas? That's me genuinely fishing because it's an unanswered question. So that is something that we're going to also have to deal with, is how to set hyperparameters is not an answerable question. Some people check all possibilities and see how it goes. Some people do what's called meta-learning, where essentially they take a gradient onto this. They do essentially the same learning technique, but on the hyperparameters. So you see, people are trying stuff, and there's some wacky ideas, but really it is unknown the best way to go about doing it. And there are trade-offs in any of those techniques. So this is going to be something that's going to give you headaches, especially if you end up doing machine learning later on. This is something that is a hard problem and can make the difference between a model that works beautifully and a model that does not work at all. And that difference can be like 0.001. You need to be able to find the right answer there. So now let's do a Kahoot. So one difference about the Kahoot today is I want you guys to pair up. If there's an uneven number of people at your table, then make a group of 3. But just pair up with someone, okay? Oh. Yeah.
You see the something.
All right, going to give it another minute or so. This should give me a good idea if people are completely lost or if people are getting it. Hopefully people are. All right. I think I'm going to call it there. If you're not in yet, jump in quick. All right, cool. So let's start out. This one's going to be a little bit harder, although you will actually know the material, so it should be good. Which is a valid loss function? Is it prediction minus y cubed, prediction minus y to the 8th plus 80, prediction minus y squared, or minus prediction minus y squared, or prediction squared minus y squared?
But then if you have like
All right. Nice, nice. Good amount here. So I'm going to talk about the ones that are incorrect. So first up, we have the negative prediction minus y squared. So this one will actually go, because essentially you can imagine the difference can go infinitely. So if the difference is infinite, then this will return negative infinite. So this one has a problem that it can go to negative infinity. The one on the bottom right will not actually be able to minimize based on the distance. So if you look at it, it's actually not calculating the distance at all. What it's actually doing is just calculating whatever the prediction is minus the y squared. So what it will actually do is just choose to predict 0 all the time. If you take a look at it, that is the minima that we can possibly get. And the first one is to the cubed, which is a nice idea, except it means that if we have a negative difference, if we have prediction minus y is negative, then the loss will end up negative. So if we have a very large difference where y is larger than the prediction, then we'll end up having a very small loss. So it has the same problem of going to negative infinity. The short answer to that is you need to have, if you're going to raise this difference to a power, it needs to be even, is the short takeaway from that. and adding numbers to it means nothing. If we add 80 to it, the minima is still the minima. It doesn't need to go to 0. It doesn't need to do anything. Yeah?
Oh, so the reason the yellow one won't work is because there's no number added to it?
So the reason that the yellow one doesn't work is actually because it is negative. So if this was not negated, then it's just MSE, but this is essentially negative MSE. And this does not have a minima. They can go to negative infinity because it's the negative difference. Yeah?
And then the green one doesn't work because you said it's closer to 0.
So the reason the green doesn't work, and I'll let you convince yourself of this, but the minimum, to minimize the green one, we just want the prediction to be 0. If prediction is 0 on everything, that's as low as it can get, or negative infinity. Oh no, it needs to be 0 because it's squared. So if we get to 0, then it will always be negative y squared, and that's as low as you can get. Any higher value, and it will make something. It'll give you positive loss. Anyway, so nice. All right. Let's see. IDK, nice. All right. Next up. Given a particular loss function, data, and model, when is there necessarily a best setting of the parameters? Is it only for linear models? Is there always a best setting? Only when the loss can't be negative infinity, or only for rational value parameters? Is that my Discord? It is. Sorry. All right. Only when the loss can't be negative infinity. So if the loss can be negative infinity, then there is no best setting. We said it. We can infinitely move the parameters more and more and more and more, and it goes to negative infinity. It can't actually be negative infinity, so it can always go lower. And for the others, linear models, it's not the case. It can have a best parameter in other cases, and only for rational value parameters. Neat guess, but no. All right. So. See, next up. Ooh, clown face. All right, true or false? Two models doing stochastic gradient descent with different loss functions will reach the same model as long as the losses are both valid. These are just some examples of loss functions. Nice. So exactly like we said earlier, something like MSE will prefer to get rid of outliers where MAE will not, and that is a difference in the model that it optimizes to. So they can be different. In fact, they almost always are, actually. Sometimes they aren't. Another true or false. Using a linear model with parameters W, we can solve derivative of loss, W equals 0 to find the optimal setting of the parameters without stochastic gradient descent. All right, yes. So This is a bit of a tricky question because I'm not actually telling you how to do it. But yes, you can. When it's a linear model, the short intuition of why it works with linear is essentially there is a linear relationship between the settings of the parameters and the output. And if you think about it, essentially we are able, there will always be a linear relationship between the actual settings and the loss. So there will be a point where we hit a minima, and then going either way increases it, and it will do it linearly forever. So what ends up happening is that if we have a loss function with a linear model, we will always end up with a convex loss function. So there will be a single loss. So if we're able to set this to 0, or a single minima, and if we're able to set this to 0, we will necessarily get that. We will necessarily get the global minima. So I know that this whole time we're learning how to do stochastic gradient descent with linear regression models. We actually don't need to. And if you actually use a linear regression program, they'll just solve it automatically. They will do a closed form solution of the gradient, and they will get it right away. Yeah?
So in this situation, there would be no local minima. It would just be one global minima?
Yeah. And it would also be a local minima, I suppose. But yeah, there's one minima when we're using a linear model. Don't worry, we won't be using a linear model for very long, but if we are, we can do it right away. All right. So let's see if the clown made it. Clown, did not make it. All right, true or false again. When the learning rate is sufficiently small, we will eventually reach the minimum loss with the stochastic gradient descent. Nope. The wording here that matters is that it's the minimum loss. It's not the local minima, it is the absolute minima. When I say minimum. You can imagine we'd go into local minima wherever we are, but we would miss other minima that could be lower. All right. Egg is making it up there, and clown's back. Nice. All right. Quiz, a real question now. The gradient of a function at a point consists of blank and blank. The direction of steepest ascent and descent, the direction of steepest descent and a magnitude, the direction of steepest ascent and a magnitude, or the direction of steepest descent and a learning rate. All right. Yeah. So it is the direction of steepest ascent. Here's just is going to be a forever reminder. Gradient is ascent, and we are doing gradient descent by going down the negative gradient. That's something that people mix up a lot. Just want to make sure you got it. And the ascent also has a magnitude. The gradient is a vector. It has a direction and a magnitude. Cool. I think that might be the last question. Oh, it's not. All right. This is the last question. If we use an alternative formula for stochastic gradient descent, like below, what would happen for learning rate between 0 and 1? The weird question for you. Oh, man, I only put on 20 seconds. Well, we'll get a lot of time to talk about it, I guess. Sorry about that. All right. Woo! Nice and uniform. Adding a bit of stochasticity into this. All right. So we can see if we actually look at the formula, so let me show it up again. We can see that at any given thing, say we are directly at the minima, say loss is 0, which means that we're at some minima, then we will still end up changing the W because we're going to be subtracting learning rate times W. So we're going to be adding W times learning rate to itself. Because of this, it will never sit still. It will keep bouncing around. This is not a good thing to do, but it's very close to something that's actually very useful that we're going to talk about later. Cool. Let's see who won it. Whoever won it won maybe on luck. And skill. Richard, nice. Egg, nice. Chen and Chen, nice. Cool. Congratulations. Well, I hope that it feels a bit better. Cool. All right. So, we're not done. Yeah. You thought that was it? You're wrong. We're here until 45. All right. So next up, we're going to do some calculus, because everyone loves calculus. So we've done here a whole bunch of talking about calculating the gradient, about calculating the partial derivatives, but I'd like to give a little refresher on how to calculate gradients a little bit by hand, and this will segue nicely into how computers calculate gradients and how we're going to calculate gradients later on. So first up, here's a function. Calculate the derivative of that function with respect to x. Just do it in your head or use pen and paper. You might notice it's the same one from last lecture. Although I changed up the 4 for z. All right, and after you spend some time looking at it at least, I want you to talk in your groups about how you solved it. Focus on the mechanism you used to solve it. All right. I know that's not very much time to do math, but it's not a math test. So, some group tell me how they did it. All right? Yeah.
Chain rule.
Chain rule. Good answer. I want you to think, how did you decide how to apply chain rule? Any thoughts on that? Yeah.
Basically just find the most outer function, or how I decided to use chain rule.
Yeah, so how did you decide, not to use chain rule, but how did you decide which way to apply chain rule?
I found the most outermost function, and then took everything inside, left everything inside of that normal, and also copied it and multiplied the entire thing by that, and then kept doing that.
Okay.
Until I ran out of things to do.
Okay. So that is basically where I'm going with this, is essentially that you can think about applying chain rule, and not everyone does it this way. A lot of people go off of intuition. Essentially, oh, I know how to do this bit, I know how to do this bit, I'll chain rule them. But we want, since we're computer scientists, an algorithmic way to calculate this gradient. We're going to be calculating a lot of gradients, and we want to have a way to do it no matter what the function is. Whether we know how to calculate the gradient or not, we want our computer to be able to. So, we're going to introduce this idea of a computation graph. And it's very important for expressing machine learning models and a few other things, but it's also very helpful for doing calculus by hand if you ever need to do it. So, we're going to draw out the function that we just looked at. So this is the x plus 4 squared plus 1 to the 8th. So let's draw it out. So we have x and 4, and we add them. Then we're going to raise them to the power of 2. Then we're going to add 1. And then we're going to raise it to the power of 8. Basically, with this image, you get the core idea of computation graphs. But let's see why they're useful and a little bit how we're going to be applying these. So we're going to label each of these outputs. So this would be, this A here is going to correspond to x plus 4. Then we're going to have b, which is going to be x plus 4 squared, c, which is x plus 4 squared plus 1, and finally y, which is going to be the output. You could call it d if you want. These are arbitrary names. So these are the labels for each of the intermittent steps. And what we realize with chain rule is that we can take, say we want to calculate some partial derivative, so this is dy dx. What we can do is we can actually find the path from y to x, or x to y if you prefer, and multiply the partial derivatives of every step that we're doing. So that would be, on our first step here, would be dy dc. So if we're traveling towards x, then we do dy dc. That's that first connection between y and c. That feel okay? Okay, okay. We're going to repeat that until we reach x, and we get something along the lines of this. So we know from chain rule that this works, right? So we can just look at the expression of it. The way that chain rule works is that we can cross out the corresponding terms in each of these multiplications. This is why we write derivatives this way. If you've never realized that, we can cross them out. That is a property of derivatives. So we end up with dy dx once we cancel all the like terms. All right? So that's something we know just from chain rule. But now we actually have a graph where we can see each step. So let's try actually calculating that derivative with it. So here's our computation graph. There's our chain rule that we know, or our chain that will calculate that derivative. So we're going to start by calculating dy dc. All right? So this is going to be c to the 8th dc. Right? And what is c going to be equal to? So this is going to be 8 times c to the 7th. And what is c going to be equal to? Can anyone tell me? Well, but as a full expression, we could do it as b plus 1 if we'd like. Later on, we're actually going to not have to do that, so you can say just the full term. Not quite, not quite. So what c is going to be equal to, we can actually see its value on the computation graph. Later on, it will click why I'm doing it this way instead of putting it in terms of b, but let's just say we can calculate what c is. We know the value at c, which is going to be x plus 4 squared plus 1. So that's the value there. So then if we substitute this into our expression for the derivative of y with respect to c, we get that. So that is dy dc. Now, I want you in your groups to play the same game and calculate the full derivative just by calculating each of these terms. All right? Go ahead. Get some practice with it. Later on, you'll have much harder functions, so get used to it. All right. Just because I'm running a bit behind, I'm going to cut it off there. I'm also just going to tell you the answers. We're not going to go do it out by hand, but similarly apply this rule, and we can see that we are going to get, the next one is just 1, and then times 2x plus 4, then times 1. So that's all 4 of the chain, and we can get our answer, which is just that expression right there, which you can simplify a little bit if you want, but that's the expression. So basically, what you've now done, if you understand this, is you understand how the AutoGrad library works. So this is how it works. You construct a computation graph, and then you calculate everything backwards until you get whatever derivatives you want. And that will give you the entire gradient basically all at once if you do it in parallel. So let's look at how this would be in an actual useful context. So recall that our model is something like this. I changed it from being a square because that's a nonlinear model, and let's just use a linear model. So we have w1 x1 plus w2 x2 plus b. This would just look like this, where we have x1 times w1, x2 times w2, sum them up, and add a bias. So this would be our computation graph for our model. Not that bad, and if we go to calculate each of the partial derivatives that we want here, I'll let you guys do this on your own if you'd like, but they end up being very easy. Essentially, we're just adding stuff together and multiplying them, and doing the derivative of that is very easy. And we end up with derivative with respect to w1 is just x1, with respect to w2 is x2, and with respect to b is 1. So those are our partial derivatives with respect to the prediction that our model is making. That's not our whole story, though. We need the derivative with respect to loss. So let's look at the actual case that we're actually doing gradient descent with, which is our model. This is our prediction is at this step y. And then we're going to remember that we're going to use this loss function, which is MSE. And then we're going to subtract the y value and square. So this is now our entire thing. And we can calculate so we see that our gradient, these are the values we care about. So we calculate each of these. And we can see that when we actually go to do it out, all we have to do is multiply the derivative of our prediction with respect to our parameters times the derivative of our loss with respect to our prediction. This entire thing ends up netting us -2 y minus y prime times x1. And then correspondingly for w2, it's the same thing times x2. Again, we're running a bit low on time, so I'm not going to walk through it, but you can try this at home, and you can see that those are, in fact, the values you get. One other thing I want to point out is that we would actually get a different derivative if we swapped MSE to have y prime minus y. The actual loss wouldn't be different, but the derivative would. So this is an important note, and that will probably at some point come up where you have your thing is learning and it's getting really high loss, and it's probably because you're using MSE and you forgot to do the negative correctly. So just remember that. That might come up in the first homework for you. Cool. And I think I'll skip over this because we're right at the end of class. But basically, we can use a matrix notation to condense all of our computation graph into a single dot product. And this is going to be our new notation. I'll go over this again starting next class. But basically, we can see that we can take the derivative with respect to the entire weight matrix, and we'll get a vector x. So instead of doing this all as individual values, we can do it now as matrix multiplication. And being like us calculating these derivatives now, we'll be able to tell us that w transpose x, which is something we'll care about later, has a derivative with respect to w of x. This is going to be the basis of all of our neural networks. So this is something that will be important. I know I'm kind of rushing through it now, but we'll see it again in the future. All right, and a little bit of advice before we end. We're right at the time, but I'll be quick. One,